So thanks for coming back after lunch. Most of you, a few not here, but that's okay. I'm going to continue what I started talking about on Monday. So today I'm going to talk about runtime verification, but I'll give a little bit of more of an overview between the differences between design time and runtime, and talk a little bit about that. So what we'll do for runtime verification in autonomous CPS is, in essence, take whatever a controller might do. So even if that controller has been designed using machine learning, let's say as a neural net, maybe we can't formally model it. So take whatever it might be doing and creating a control input for some plant in a CPS that we're trying to get to do something, and then analyze what the behavior of the plant would be under that control input for some amount of time. So basically analyze a bit into the future. And in doing this, if we have, as we'll see, sort of a backup strategy for if something will go wrong by doing that, then try to recover. So that'll be the basic idea. And of course, feel free to stop and ask if there are questions. So of course, we're trying to verify properties. And this is what we sort of do as the dominant effort within engineering, particularly within CPS. So just to review that briefly, although we've heard quite a lot about it, particularly in the context of hybrid systems models of cyber-physical systems. So I'll just talk a little bit about what this means in the context of this talk and in runtime verification. So it may not be possible to solve this problem a priori, like when we're building a system or writing a program. But our model of a system here would be a feedback control system, such as would arise in CPS. And instead of doing this at design time, we'll do this at runtime to try to check if it's doing, ideally, provably what we want it to do. All right, so let me put a little bit of this in the context. I want to talk just briefly about our sort of notional ship platform in a little bit more detail, since I had to skip over that on Monday. So just kind of a platform to keep in mind, and I'll review the types of control architectures we might have. So the previous talk on adaptive cruise control, cooperative adaptive cruise control, those type of systems we're actually also currently working on, not on the cooperative aspect, but on doing adaptive cruise control. Right now as a part of a DARPA Assured Autonomy project that I'll mention briefly, where the goal may be that that adaptive cruise controller has been designed using machine learning. But within this notional mental model that we'll discuss briefly, so we have some autonomous, in this case it's a surface ship. We're working with a team that develops sea vehicles in this DARPA project, so we came up with this kind of idea. But you can imagine this is a car or whatever. It's not super important. So we have some system. It's modeled in a planar way, so it has positions and then some heading. And we'd like to get to some target destination while avoiding some obstacles. And then we may have some performance criteria, which will become important within the context of this talk. So try to minimize time traveled or distance traveled or whatever, while always avoiding obstacles. So it may be the case if we're really doing this, say, in an autonomous ship or an autonomous car, where we may need to be using some perception to estimate the sizes and positions of those objects, right? So there'd be some maybe vision methods that are trying to come up with where those obstacles are located, ideally with some accuracy and precision, and then how close we are to them. So we'd like to avoid these obstacles and get there while minimizing time. So the types of architectures to keep in mind, we may have some perception. So I'm not going to really talk about how we might do something with that, although whatever this perception module may come in to our controller as we try to control, in this case, a plant that's being disturbed by, say, waves or wind or whatever other perturbations in the environment might exist. whatever this whole sort of module is going to do, that'll, in our case, in this ship control example, come up with, say, a speed and a heading, or an acceleration and a heading. For simplicity, well, let's just think of speed. So we can directly control velocity. So whatever types of control inputs to the plant we come up with, how can we check if those are going to meet these safety requirements, at least at runtime, so avoiding obstacles. So that's the kind of model to keep in mind. So just a couple differences between these types of approaches and what we mean by design time and runtime verification. So design time, we're essentially doing it when we're building the system and we're testing the system and we're trying to characterize the behavior of the system. So we do that during the development of the system, typically prior to deployment, depending on what kind of a software systems engineering model is used, whether it's a V model or maybe some more agile model. We're trying to do that as we're building the system, and that's typically offline. Whereas with runtime verification, we'd like to do this while the system is operating. So maybe during its deployment, so this is online. And in the context of CPS, the computations, if we're going to possibly interfere with the control inputs provided to the plant, we may have real-time requirements on this, and that'll become clear shortly. The other thing in the context of autonomous CPS to keep in mind, and even in non-autonomous as systems get bigger, design time just simply may be impossible for a variety of reasons. Scalability of model checking algorithms, reachability analysis, these things, then we simply may not have models, right? So in some of the previous talks, we had black box testing approaches, or maybe the models are just going to be a bit too complex. So ideally, with runtime verification, we'll be able to formally check whether some properties are true, but maybe we're just monitoring, right? So you can think of it as sort of trying to detect anomalies at runtime as well. But what I'll talk about will be in more detail today will be a reachability computation. So we'd like to have provable guarantees if we can. So I want to give a quick reference if people are interested. We're going to have this on archive soon, but this summarizes this paper, what all the state of the art is in verification of autonomous systems, particularly doing things like reachability analysis for neural networks. Also, so some of the design time methods for analyzing machine learning-based systems, particularly kind of tuned into autonomous cyber-physical systems. So also some runtime monitoring approaches, which I'll talk more about today. But I just wanted to point that. So a little bit more in the context of where things are at with offline and online verification. So there were a couple of CAV papers last year on analyzing neural networks with a form of piecewise linear activation functions. So that's primarily what's been focused on. And I'm going to talk more about those types of systems on Friday. But these ReLU activation functions, which basically take a max of a linear function and 0. So they're very slightly nonlinear, but essentially piecewise linear. So we have some work beyond these types of activation functions, and then some other work in this context for design time. So for online, what the papers behind what I'm talking about today are based on this TEACS and RTSS paper from a couple years ago. So there are a few implementations of this reachability algorithm, which it's nice that Tao's here because it's essentially facelifting, which I don't know if you're aware of this work or not, but this uses facelifting. So so that reachability algorithm. So if I say anything wrong, please correct me. But there's a couple implementations of this, and when we did this work, so this essentially, as far as I'm aware, is the only reachability algorithm for hybrid systems models that can be implemented with real-time guarantees. So many of the systems require a large set of libraries. Maybe they require recursion. So this implementation uses no data structures beyond structs in C. And we've also now completed a Java port of this to a distributed robotics platform. But I'll show you some results of actually implementing this in several different architectures. So the implementation is simple. It doesn't use any fancy geometric data structure libraries, which many of the offline or design time verification and reachability analysis methods would. And I'll talk about why that shows up later. So just a few pointers to other things going on in this area. So there are a couple DARPA programs related to this. So we're involved in this Assured Autonomy program. And the goal of this is essentially to get to a point where we can trust autonomous cyber physical systems. So how can we do that? So enhance trust in them. There's some other programs such as DARPA's Explainable AI program, trying to understand either the internals or at least the outputs of what some of these machine learning methods may be doing. And the talks on L-star learning and things are quite nice because those are, in some sense, sort of a more understandable form of machine learning versus the currently very popular deep learning paradigm, which is sort of purely statistical and has maybe even more challenging than understanding a state machine that has 50,000 states and 1 million transitions. So then there are a variety of long-term challenges here that some of these some of these programs are trying to address, such as what does correctness even mean within machine learning components? Do we need new specification languages? So I think that's going to show up more on the perception side than on the control side. I mean, how do you even write down what it means for, say, an image classification algorithm to be correct? It's very strange, right? How do you talk about it? I mean, I can say it, like it should never classify something incorrectly, right? So it should never tell me that a picture of a dog is actually a rifle or something. And it turns out, I mean, you laugh, but if you if you aren't aware of all the work going on in adversarial machine learning right now, there are attacks on all of these types of deep learning-based systems where you can apply inputs that will do just exactly that and automatically find those inputs to break these methods. So how do we specify that? So the perception thing, I think, is a bit farther out. Now, for the control side and decision making, some of the existing specification languages like signal temporal logic and planning languages as well may make sense, or even just kind of automata type of a language for specifying behavior. Right. So that's what I wanted to mention. And let me, I think I rearranged something. Yes, okay. Okay, what I see is different than what you see. Okay, I'll just scroll forward. Okay, all right. So runtime verification for these types of systems. So in essence, something we can do is quite simple. It's just supervisory control. So that's essentially what I'll be talking about. So the framework of what this is called runtime assurance. And the particular architecture is known as the Simplex Architecture or Simplex Supervisory Control. There is some loose relationship to the Simplex algorithm, but the name is not really related to that. We just have this issue with naming things in these areas. So essentially what we'll do, we have some plant we're controlling. We have some complex controller, maybe it's machine learning based, with some deep neural net that's been used in there. And then we have some other controllers. In this case, I just have one shown, say a safety controller that'll take some mitigating action. If we determine that whatever this controller, whatever command it would apply to the plant is going to cause us to violate some of our properties. So this decision module then should be able to make that decision in a timely enough fashion to be able to fall back to this, perform a safe action. So the general framework makes sense? Good, all right. So the core of this is doing reachability analysis with real-time guarantees, and that comes into play with making sure that we can do this in a timely enough fashion. So let me just briefly talk about Simplex Design. So this has been applied in a variety of contexts, but basically we're going to monitor some controllers we don't totally understand and fall back to some other controllers. So the original application of this was in aerospace around 2000, and apparently the FAA accepted this as a certification argument where previous versions of flight control software would be run in parallel with new versions. And rather than going through the process of certifying the new flight control software, you'd certify a decision module, and you'd already certified your old flight control software. So if this had been certified and this is certified, as long as this, again, can switch over to the previously certified controller, you can run a new version in parallel. And ideally use that new version of software as much as possible. So I'll talk about that in particular because there's a reason there's some new version of the flight control software. Maybe it's using new fancy neural net things, whatever. But typically there's going to be some performance criteria of why the complex controller exists. So we'd like to use it as much as possible. So trying to maximize the usage of it is a key point because otherwise, I mean, I can clearly satisfy safety just by always using the safety controller, right? If I already know that that has has an ability to meet the specifications, the safety specs that we would have. So that's kind of the key challenge is how do we do that decision making? So again, that's the basic issue. So the safe design is easy. We would just always use this. So reducing the conservatism in the decision module is the key challenge to overcome. And it turns out the typical ways that you would have come up with that decision module, they're based on Lyapunov-based methods that you do at design time. But the problem with that, as we'll see in a minute, is sub-level sets of quadratic Lyapunov functions are ellipsoidal. And your constraints or your specific specifications may not be. So we'll wind up with not being able to use our complex controller very often if we had done this offline. Questions? Are we on time? Okay, pretty good. Right, so I use a running example now of an inverted pendulum. So the goal of this is to stabilize this rod vertically, and there are a few state variables. There's a position of the cart. Basically, we'll push the cart back and forth to get that arm to stabilize. And there are some safety constraints here that we don't want the arm to go too far down, because if we do, the motors that we have controlling the wheels of this may not be able to generate enough applied force to be able to swing that arm back up. So there are ways to do that, but in this, keep that in mind. Some other safety constraints that exist would be there's a finite track length. So we can only push the car to, so far. So there are a couple ways that you could do this. So one way you could do this is offline. You could imprecisely characterize the recoverable states. And what recoverable states are those that you can show, in this case, by just having discretized the state space and running a simulation with the various constraints that exist on the system. From that point, can I get back to the equilibrium point? And the overall goal, this is a 4D system with the position and velocity, and then the angular position and angular velocity. So the equilibrium point of the origin is where we're trying to get, while maintaining some constraints that I'll show in a minute based on lengths of things. But can we go from these points and still stabilize? So this is sort of an approximation of a region of attraction with these various constraints that would exist. The motors are not infinitely powerful. They can only produce so much torque, which then corresponds to so much force being applied to the to the card and then to the arm. So how would this scale? So obviously this is not a formal way of doing this. There would be accuracy issues. There could be points between simulation points. But the biggest problem actually is if you characterize this and say built a lookup table, or maybe even tried to interpolate between points, how many points do you have to store? And it's going to scale really quite terribly in the dimensionality of the system. So this is a 4D example. So if we were to partition that space up, so taking points within that satisfy the constraints and then checking if we can recover or stabilize from those points or not, we'd wind up having to run a ton of simulations, even for a quite simple system. So we'd spend a lot of time simulating, but then the bigger problem is if we were to use this and say, okay, I can use the complex controller from any of those points because I could recover or stabilize from them, how would I then store that at runtime? And that would be quite problematic. So the scalability of this with respect to that of, say, building a lookup table and then checking if the point that we're currently at or the point we're closest to would be safe or not would be quite bad. So if we had 100 partitions per dimension with an 11-dimensional system, it would be pretty terrible of how many simulations we'd have to run. And the assumption is here that each simulation takes a microsecond to run, which may not be reasonable. So if we were to save all of those safe points and then try to use this online with a lookup table, we'd run out of memory, right? We wouldn't be able to do this. So instead of doing that, instead of simulating points and checking if these points are safe, we will compute reach sets at runtime. And this will overcome many of the limitations of even if we were to run simulations at runtime. So for example, this will account for numerical inaccuracies, approximation inaccuracies, the choice of which point we're using. So as a hybrid automaton type of model, which we've seen several examples of, you can think of it roughly like this. So we have a safety mode, we have a complex mode. When we're in a safety mode, the dynamics of the system evolve according to some ODE specified by that safety controller. When they're in the complex mode, they evolve according to something. We don't even need to know what this is, right? This can be anything. We would need to have some characterization on this because what we're going to do is compute the reach set when we're using the safety controller to see if that's good, or compute the reach set when we're using the complex controller with whatever control input it would have come up with. And then if we were to switch back to the safety controller, can it still recover? So that's the basic idea. We'd fall back to this with enough time. And I'll show a few more pictures that'll make that make sense. So a few other things, there may be some constraints on when we would go back and forth between these. That would be defined by a few things. The timing model we're assuming is periodic control. So we have some clocks that are evolving and switching periodically back and forth between these. There are a variety of real-time scheduling models that can be incorporated, but basically we'll check this every delta time. So we'll do some reach set computations essentially up until the next point where we would make a decision. So where this becomes important, and in contrast to how most of the reachability methods for design time are working now, we don't care about long-term error control in the reachability method because we really only need to do it up to the next time. Okay, so that'll become clearer in a minute. Okay, so I'll skip this because we've heard lots about reachability. All right. And we've heard about accuracy. Okay. So how can we do this? So what defines the best switching logic or the best decision module for us? So let's suppose we have some unsafe set of states or some bad set of states. So we'd compute up to some amount of time what the plant could do under whatever input the complex controller has come up with. And then we'll compute the reach set from that by applying the safety controller. So basically what this lets us do is whatever the complex controller did, if at the next time interval switching to the safety controller, if then if we would still have problems, then definitely or potentially we could be unsafe. But if we didn't intersect any bad states, then it's okay for us to use whatever the complex controller came up with for the next time interval. All right, so I have another picture. And there's another way you can formulate this in terms of backwards reachability. Okay, so another thing that you could do is maybe use a reachability analysis tool such as FlowStar. So again, we have someone in the room somewhat related to this. So this is good. So we could do this type of analysis at design time and compute these reachable sets of states offline and then encode these. So this is similar to the lookup table idea with simulations, but now instead of doing that, checking offline if reach sets could also work from different points. So a variety of other representations of sets of states that we've seen. So the problem now with this is that the representations of the sets of reachable states, again, may result in being infeasible to put onto an embedded platform. So even for, in this case, an example that's a 9-dimensional biological model with nonlinear dynamics and lots of nice features, if we're only looking 10 steps into the future with a variety of parameters, the reach set that we're getting out for that short time horizon into the future is already 3 megabytes. So if we were to try to encode all of this in some way in an embedded platform via lookup table or some other way that we'd check if whatever state we've currently sensed that the system is at, if it falls into one of these sets or not, it'd be difficult to try to do that. Obviously, memory constraints are always decreasing, but still a bit of an issue. So the other approach of how this has been done is based on Lyapunov analysis, again at design time. So for linear or linearized systems, the dynamics of this pendulum are technically nonlinear, but around the equilibrium point, you can come up with a reasonable set of linear ODEs. You can formulate a control design problem where you'll come up with a specific type of controller. In this case, it's a linear state feedback controller as a form of linear matrix inequality optimization problem. So these things would all be inputs, and then we can find a Lyapunov function and a gain matrix such that the system is stabilized. So then we can use the sublevel sets of that Lyapunov function to characterize the region of attraction of the system. So this is sort of an abstraction of doing reachability, since the sublevel sets of the Lyapunov function would be positive invariants, so we wouldn't leave them over time. So this is basically what this would look like. For this particular system, or any abstract system, if I wind up with this form of quadratic Lyapunov function, and if my constraints, so say my safety property, and if my other types of operational constraints that I may have, such as my track length being, let's say, -1 meter to +1 meter, oftentimes they're going to be linear constraints. And when you try to fit an ellipsoid into a box, especially in high dimensions, the amount of space that you're missing, the amount of volume you will not be able to cover, so the difference of these points and the points in the ellipsoid is going to get bigger and bigger. So essentially what this picture is saying is that anywhere within this ellipsoid, we can use the complex controller. And anywhere outside of it, we don't know. It may be okay to use it, it may not. So pictorially for this system, this is essentially what this would look like. So this is a sublevel set of the Lyapunov function for a particular gain that we found. Again, for the pendulum system, centered at the origin is the equilibrium point. So this is where we would say we could use that complex controller. But all of these points, it turned out the green ones were okay to use. So at least by doing some simulation-based analysis, we were still able to recover if whatever the complex controller had done over one time period required us to switch over to the safety controller. So really, we could have used the complex controller anywhere in the screen region. But with this type of offline analysis coming up with a Lyapunov function, we'd only be able to use it within this region. And essentially, the difference of how this thing is going to scale between the area covered, or the volume covered by the ellipsoid, and some, in this case, box, the scalability of this is going to get worse and worse in a higher dimension. So there's going to be more and more volume where we wouldn't be able to use the complex controller. So more points in the state space, we can't guarantee that the system is actually safe. How am I on time? 10 minutes-ish? Okay, all right. Okay, so let me try to wrap up in the next 10 minutes. So this is what we do. So we're going to combine aspects of that Lyapunov-based method with real-time reachability. So basically, if we know we're inside of this ellipsoid, we're already done. We already have a proof, essentially, that we're good to go. But for points outside of the ellipsoid, and checking this is quite easy, right? There's some multiplication and addition operations. So checking that constraint, which tells us if we're at a point X inside of the ellipsoid, is easy to do at runtime. So we'll check that, so we don't need to do that for too long. And then we'll compute reach sets up to the next time we might be able to switch controllers, which is every delta time. So in essence, what's happening, there will be some region inside of this larger ellipsoid where it'd be okay to use this, and then we're going to be checking these other points. So we'll do this reach set computation online instead of offline. So the benefits of this is now we're no longer limited to this ellipsoidal under approximation of the region of attraction. And we don't have to do any of this enumeration, like doing simulations offline a priori or computing reach sets offline a priori. And then using the method that we're going to use, because we don't care about computing reach sets for long periods of time, we don't actually have to use a complex state space representation. So we're just using hyper boxes or hyper rectangles. All right, so that's the key idea. So we'll let the system go outside of the ellipsoid as long as we can establish at runtime that none of our constraints will be violated and that we can get back inside of this, right? So if we can't get back inside of it, then there could be a few problems. So just to show you what this looks like for this example system, in this case, some slice of the 4D space, now the angle and angular velocity. So our safe ellipsoid is this cyan region. Then the points that we determined at runtime are safe to use are now all these green regions, and an estimation of the optimal is are the yellow points that we determined with simulation. And then the red points, we couldn't establish this, or maybe we were violating a constraint. So this is based on this mixed facelifting reachability algorithm, which, as you can see, is now 20 years old. And the key idea is that performing the computation in a quick and deterministically characterizable runtime, so we can come up with real-time guarantees, is more important than doing long-term error control. So there's a little bit of assumptions that would come into this, particularly some bounds on the derivatives of the ODEs. So the real-time aspects of this, of how we can implement it with real-time guarantees, is it has no dynamic memory allocation, no recursion, nothing fancy, no libraries beyond standard lib. It's also an anytime algorithm, so it's going to use as much computation time as available based on whatever our control period is before our deadlines are exhausted. And then we've tested this out. So one of the inputs to this, let's say this is a vector field for our system. the user needs to provide a function that would bound the derivative if we were to place an arbitrary box. So essentially, we've got to be able to characterize some function if we were to put a box on top that'll give us extrema of what the derivatives could be inside of this box. So what's the basic idea? So the basic idea is the name, which I think is a quite nice name, will essentially lift the faces of the box representation. So we have some representation of the states that we're at, or the set of states that we're at, and then according to the ODEs of the system, we'll move the faces of the box. So essentially, we'll come up with some new set of states that we could get to after some amount of time by following the ODEs. So you can do this for each face of the box. So say that the vector field along this line is defined by this. Because we have a bound on the derivatives, we can determine how far out we're going to need to push this along any point in that, along that line. And the way the computation is working, we're computing this out forward into time, some desired time step or desired step amount of time. So we do this pushing out of all the boxes, possibly inward, depending on what the values of the system dynamics are. We do this for all of the faces. And there's construction of neighborhoods of the faces. So basically, how far out are we going to go along each of the faces, or potentially inward? Let me see how much. I've got about 5-ish minutes. So there are a couple details. So because the vector field potentially could be changing within this neighborhood, right? So at this point, the vector field might be different than that point, or maybe it changes direction, right? So maybe it was going out this way, and then all of a sudden it's coming back inward, or it was going inward, and then it changes to be going outward. There's a resampling step that has to occur to check for that. So if the neighborhood would change from being going inward facing to being outward facing, so the intuition of that again is the idea that we had been going inward, but now all of a sudden, based on the change in the vector field, we actually would need to push outward. We would need to redo this computation. And then there's another piece which I'm not going to talk about in too much detail, just given the time, if our estimated widths of these boxes had doubled in size. And this has to do with the choice of parameter in our algorithm. So we'd compute this up to the time until one of the faces would leave its neighborhood. And then we'd advance time further up until, say, our control period that we care about, and then repeat. So we'd come up with this new box from wherever we had been at. So that's the basic idea behind the reachability algorithm. So then there are a few properties of this. So there are theorems in our papers. But basically, this allows us to provide real-time guarantees on the computation. So the construction time would be bounded. You can establish this doubling. The reasons we need to redo the computation can only happen a finite number of times. Numbers of iterations would be bounded. So there's a way that we're changing the time step that would cause that to occur. So then it's linear to advance this in time according to the dimensionality, but one of the reasons this isn't used at design time so much anymore is because this winds up having a lot of error if we're computing reach sets far into the future. And this is due to an effect known as the wrapping effect. So, but the point is, if we're doing this at runtime, it doesn't matter, because we only need to compute so far to a horizon so far into the future. And then what are we going to do? Well, we're going to get a new sample point. We're going to know where we're at, right, almost immediately. So it's kind of similar to model predictive control. So because everything is implemented periodically, we get new sensor values periodically, we know where we'll be at some next time point, so we don't have to keep going too far into the future. So this is in the anytime part. So we do this with some fixed time step, and then we'd recompute if we have more time available. All right, so let's talk a little bit about that. So this anytime aspect, based on using different repeatedly smaller time steps, we'll get finer and finer approximations of the set of reachable states. So starting from this point, if we used time step of this size, we'd wind up with this kind of big region. But if we had more time available, we could actually get a quite fine approximation of the set of reachable states. So we can iteratively improve this if we have enough runtime available. So how does this compare in this type of system, which previously had been designed using LMI-based Simplex? So this is a plot I showed earlier. So these green states now, we'd be able to use the complex controller safely. It's not quite optimal, but pretty good. So that case is not so extreme, but this picture illustrates better the problem raised of trying to fit an ellipsoid into a box in high dimensions. So essentially what this represents is some corner of this 4D space where we tried to fit an ellipsoid into it. And this is the only region where, if we'd done this Lyapunov-based design, where we'd be able to say that we could use a complex controller. So it's sort of a small region. Whereas if we were to do this real-time reachability approach at runtime, we'd be able to use the complex controller much more frequently. So just some runtime comparison. So for this particular system, how much more can we use the complex controller? That's a function of a few things, but primarily the amount of runtime available to the real-time reachability algorithm. So we can approach optimality at around a second or so of runtime available, in this case on a modern i7 laptop. Whereas even with a fairly small runtime, we can still use the complex controller quite more frequently. And this is just estimating the volume of the state space where we could use the complex controller. So these are numbers of points. So what about on more appropriate embedded platform like ARM? So for somewhat reasonable runtimes, we can still get quite a lot of improvements. So again, we could use the complex controller quite a bit more. Not quite as good as in the i7 case, but obviously still reasonable. And then we've even done this on Arduino just to sort of implement things or sort to illustrate the portability of this. Because doing it on ARM and i7 is maybe not that exciting, but on Arduino, the particular Arduino had software-based floats as well, which is introduces a lot of systems issues. So if we're using 100 millisecond runtime, we weren't really getting much of an improvement, whereas if we're using longer runtimes, like on the order of seconds, we could still get some improvement. But that one was sort of more so to illustrate the portability of the implementation. So the basis of trying to do runtime verification and runtime assurance, so trying to ensure some safety specifications at runtime, without regard to whatever a controller might be doing, has been illustrated in this. So the kind of key contribution of these papers was really this reachability algorithm, but then it turns out as the various issues we see in trying to use machine learning-based components within CPS are showing up. It also can provide some capability to do some analysis of those types of controllers, because it doesn't care what the controller is doing. Now, obviously, to ensure safety, we need to have a strategy that still works. So that may not always be the case. So for an autonomous vehicle, stopping may not actually be a safe response, but for some systems, stopping, let's say, might be. Some other things that have happened recently, we've written this in Java and integrated it with our distributed robotics control framework, which I showed a couple pictures of last time, but that's what this looks like. So we're computing reach sets of these things at runtime now. And there's some interesting things that show up when you try to do that. So computing reach sets for a distributed set of agents and then combining them back to try to provide some guarantee on the global behavior based on local observations. So it's some recent work, but some things we're doing with this. All right, so I'm out of time.
Thank you very much.
Thank you.
Any questions?
On page 73.
Oh, a lot of slides. Well, I skipped a bunch, right?
Yeah. Yeah. You show the green and the red region, and they overlap a bit on the left side. How does that? Is there a graphical problem?
Yeah, it's a graphical artifact. Yeah.
Okay, so it's not that the real-time reachability tells you something else than the simulation.
No. Yeah, the simulation is in essence optimal. Yeah, I mean modulo some numerical artifacts. Yeah, it's just an issue of plotting.
Okay.
So the way these plots are generated, we're doing like a sampling and running simulations from each point. And then for the reachability, we're doing something similar because we could start from a set of states. We can bloat the initial points that we start from, and that would account for numerical things.
I have a related question. There's two communities. There's the validated numerics community and there's the reachability analysis community. And the validated numerics community, they pay a lot of attention to upward rounding and downward rounding so that when they compute something, it's guaranteed to include the exact mathematical trajectories. The real-time reachability analysis that can be done today, does it do all this upward rounding and so on? Okay, so it's not guaranteed in the same way, but with some margin, then you get a kind of guarantee.
Right. Yeah, so it's not necessarily accounting for numerical issues like due to floats.
It's already really impressive that it can be done in real time. If it could be done in real time with all the upward rounding and down rounding and so on, that would be really pretty amazing.
Yeah, I don't think so like the naive thing you could do is replace floats with like an arbitrary precision float or whatever, like with big num or something. But then, but then that's a list.
It's a dynamic
or
structure.
Something, right? So then, immediately.
So another thing that causes complexity in terms of runtime is splitting. So a lot of situations when you have events, for example, and your set meets another surface at different times, then you split that into two cases and then you start simulating those. How do you avoid that?
Yeah, so this hasn't really shown up in the hybrid case so far. So for what we've looked at, obviously this is an issue, but the things that we've done, essentially it's a continuous system.
Okay.
Yeah.
Okay.
Yeah, there are other issues that come into play when you'd have switching. And the runtime verification community has worked a lot on this.
Okay.
Yeah. So the discrete aspect of this is sort of trivial at this point. Yeah. So those. So I don't know. It's good future work.
Very, very interesting. Very interesting. Thank you. Other questions from the audience? Yes.
So I saw that you consider platforms such as ARM and i7 and even Arduino. But have you considered, for example, FPGA platforms, and more specifically those low-end FPGAs, such as the Xilinx, Zinc, or whatever?
Yeah. So once you fix everything, like you fix the system, you could do that. We haven't done that. We've thought about it, but I think that could be done. Yeah.
Because you can significantly increase the throughput and output.
Yeah. Yeah, particularly for some of the computations that are occurring, it could benefit. Yeah. Again, it's just it's something that could be done, but not something we have done. So the issue with doing that, then, one of the issues with that would be if you do get into the hybrid case, then things are like with more discrete stuff, then things are going to become a lot more complicated. Yeah, so for that, I don't know if it would work. But for what we're doing, once the dimensionality is fixed, then essentially the boxes are all fixed. So, the number of entries in the boxes are fixed. So.
Any other questions? Great. Thank you very much, Tyler.
All right. Thank you.